Welcome back. Bitcoin lightweight clients. So you can imagine the blockchain, as the blockchain is accumulating all transactions that are happening on its ledger, it's probably growing quite a bit. And yes, so the mainstream will probably not be able to store over 300 gigabytes of data for a simple wallet. So we need some kind of a lightweight client in the sense that it's less CPU intensive, it's less network intensive, it's less storage intensive. Because we know that the mainstream will probably not use a substantial CPU power to validate transactions of other nodes. So in a sense, you're only concerned, as a lightweight client, you're only concerned about your own transactions, and ideally you want to have some other participants that will be giving you transactions, will be giving you your transactions that are only relevant to you. So the dilemma here, however, is that we want these transactions always to be secure, right? We don't want to compromise security for convenience. So the scaling problem for lightweight client is really that the log of transactions is big, right? Depending on the blockchain that you look at. And the mobile phones, they receive irrelevant transactions. So these are sent basically here. If you send a transaction in this peer-to-peer network, then many of these peers receive transactions that are not necessary for their operations. And you obviously have limited data traffic over 3, 4, 5G nowadays. So this is something that Satoshi Nakamoto thought about in the original Bitcoin paper, and this is so ingenious. So we have here the blockchain, so where you have the headers only, right? So let's say we have block 1, 2, 3, 4, and we only have the headers. So the header contains the proof of work, right? So the header is only 80 bytes in size. It doesn't contain the list of transactions. So basically, with the header alone, you can verify the proof of work, and you can find the longest chain with the most proof of work. We will be discussing proof of work in a later lecture. But basically, what you can think of here is that by only having the headers, and this is a lightweight client, this is quite feasible to be stored on a mobile client. And what's also interesting is if we want to verify the validity of a transaction within this header, we can do so. Remember the Merkle tree in the crypto part of the lecture? So if we have a transaction here and we want to know whether this transaction is in the blockchain, is this included in the blockchain, then all we need to do is to get the other transactions of the block that are relevant to construct a partial Merkle tree to walk up to the Merkle root. Okay, so I repeat. We have this particular transaction here, this transaction that we want to verify its existence in the block, in this particular block. We don't have the full block, we only have the header. So what we're gonna need is this particular transaction. We're gonna hash it, right? Given its hash, we're going up here. And then we need another hash, which we have to request from another peer in the Bitcoin network. It's typically this data is provided by the full Bitcoin nodes. And given only these two red encircled data points here that we have, the hash and the transaction, we can compute here this hash and the Merkle root hash. Now, this Merkle root, this one, is included in the header. And we can verify whether this one is correct. So if they're equal, then this means that, yes, this transaction is actually included in the blockchain. So this is called the simple payment verification scheme because it's simple, it's lightweight, and it allows you to verify whether a transaction is actually included in a block or not. Thank you very much for watching.